Okay, well, let's make a start. Okay, hello everyone. Welcome to the March 2024 A3D3 seminar. I'm very pleased to be able to introduce today's speaker, who's David Hogg. David is a professor of physics and data science in the Center for Cosmology and Particle Physics at New York University. He's also group leader for the Astronomical Data Group in the Center for Computational Astrophysics at the Flatiron Institute. For those of us from an astronomy background, David is one of the great leading figures in the application of realistic machine learning and sort of those sort of techniques to a lot of the big data problems in astro. David's main research interests are in observational cosmology, where he likes to use galaxies to infer the physical properties of the universe. But he's also done a lot of work on the properties and kinematics of stars and exoplanets. And David's talk today is about whether machine learning is actually good or bad for astrophysics. So David, please take it away.
Thanks very much. I'm trying to share my screen. I should see if this works. Great. I have to open system preferences. I have a brand new computer, so I have to somehow allow it to. Yes, good. Great. Let's see if it works. I gave it permission, but it said I might have to quit and reopen. Oh, no, it looks like it's going to work. Looks like it's going to work. I'm feeling good about it.
Yep.
That's visible?
Yep, we can see.
Good, great. Let's see. I can go to slideshow mode.
Yep.
Good. And you see these slides?
Yes.
Okay, good. This is I'm focusing on astrophysics, but I think everything I say here applies to a lot of different areas of science. I don't think it's particularly astrophysics-y, but astrophysics is my domain, and so I can be more specific there. I'll try not to be too jargony, but there'll probably be some moments where I get a little astronomical. So feel free to just say something in the chat if it's a little ugly. And I'll try to respond. I'm trying to monitor the chat, but Matthew, if you'd keep an eye on the chat too, in case I miss something.
Yeah, will do, David.
Okay, good. Good, let's start. Oh, and my slides are visible at that link. I think it'll work, but you'll find out the hard way. Let's see. Here we go. Is this working? Yeah, good. Okay, great. So basically what I'm going to say is that the thing that's interesting about machine learning methods is they can't really be trusted. They're not trustworthy partners. And because they're not trustworthy partners, when you use them in certain places, they can give you bad biases or systematic errors. So that's kind of, if I really had to summarize the negative side of my talk, it's going to be that. The positive side of my talk is that actually you can use untrusted systems all over the place. And in fact, we do. In all sorts of things. Actually, machine learning isn't new here. Astronomy is built on history of doing remote sensing with like CCDs and infrared detectors and things. And like the current generation of infrared detectors, nobody really understands how they work exactly, but we can totally use them. So we do make very precise measurements with infrared detectors, even though we don't quite know what all their properties are. So I think it's interesting that machine learning cannot be trusted. That's a big red flag. But at the same time, if you structure things correctly, you can use untrusted components in a very trustworthy scientific way. And I'm going to give an example, a particular example where it's actually really valuable to have kind of machine learning point of view. Okay, good. Here we go. So one place to start, and some of you have seen this joke before, is what have we learned in astrophysics from machine learning? And the answer is right now, not very much. And I've asked this question on the internets, and various people have answered in interesting ways. And certainly machine learning is a component of astrophysics projects, but there's no really big result in astrophysics which you can point to and say, we only got that because of machine learning. Although I do have some examples that are close. And so I broadened this question to ask about science as a whole on the internet years back when Twitter was a thing. And people came back and said, machine learning solved protein folding. And if you don't know about this, you probably, in this crowd, probably everyone knows about AlphaFold, which was a very nice project. There's the PubMed link there for one of the papers. There's actually quite a few papers about it. And this is a machine learning system that can predict a protein structure from its sequence. And that is one of the goals of the protein folding community. But one of the interesting things about this success is it isn't really a scientific success in the sense that nobody learned from this how proteins fold. They just have a now unbelievably complicated black box that can predict it. And that, of course, has tons of uses. It has tons of clinical valuable uses, but those uses aren't exactly answering the question of how proteins fold. They're answering other questions like what kinds of new proteins should we be looking at for new kinds of diseases and things like that. So there's tons of uses of this thing, but it's not exactly that we learned about protein folding. It didn't really solve protein folding. It kind of obviated protein folding almost. And so that's kind of interestingly related to the things I'm going to say. One thing, and I say this in all my talks, actually, not just ones about machine learning, is that my group, I'm an astronomer. Actually, I'm a physicist by training. I'm in a physics department. I do physics experiments. Most of my work, though, is really astronomy work. And a lot of that is very much engineering oriented. We're very interested in the engineering of big astrophysics projects, like how to make the software better, how to conserve information when we do data analyses, data analysis pipelines, open science, project management stuff. We do a bunch of different things that are on the kind of engineering side of science projects. And so I'm going to make comments about engineering as we go, and I don't want them to sound at all pejorative. Sometimes when you're in a scientific audience, people hear engineering and it sounds like there's people like covered in grease, like turning bolts underneath the car. And I have 100% respect for all of that stuff, and we work on it. And I just want to be very clear that for me, this engineering is part of the scientific enterprise, and that's why we do it. And I'm saying that now because later in the talk, I'm going to talk about places where machine learning really helps us with the engineering. So one thing, if I'm going to talk about machine learning and have a grandiose title, I have to say, what is machine learning? And my definition of machine learning is actually, it turns out a bit controversial. I'm using an old definition. Actually, I should have a reference on this. This is actually a definition that dates back at least to the 80s, but I think it might go earlier than that. But for me, a machine learning method is a method whose capability improves substantially as you add more data. And by substantially, I mean kind of faster than the square root of n. It's not just that you're measuring things better, you're getting a better model space, or you're learning the model structure, or you're learning the representation of your data, or it has to be learning like more than just kind of improving, tweaking as you see more data. And so one of the interesting things about this definition of machine learning is it includes super classic things like principal components analysis and support vector machines and linear regression and Gaussian processes. I consider all of those things to be machine learning. And not everyone would include all of that in machine learning, but I don't think there's any easy place to cut except there. And of course, the contemporary methods are like multi-layer perceptrons, deep CNNs, transformers, diffusion, and many more things. But, like when you think about science, those are kind of 4 things that are making big inroads on science right now. Good. And then supervised, I'm talking to the converted here. Everyone knows about this. You have a golden set of objects. You call them your training set, where you have features, which might be images or spectra, and labels, which might be parameters. And I'm just being very, very clear here. You guys know all this, but the idea is that there's a training step where you try to find the best function. And then there's a prediction, a test step or a prediction step where you predict labels for unlabeled data. And the one thing I want to emphasize here, and I think you can probably see my pointer, the one thing I want to emphasize here is that there's a deep assumption in these kind of supervised methods that your new data are similar in some way to the training data. And that's going to come back because that assumption, first of all, is very strong and often wrong in scientific contexts. Often your good labels are for a special set of objects, not a typical set of objects. Often it's a special set. So that this assumption is often violated. And even when this assumption isn't violated, the things can have weird properties. We'll come back to that going forward. And in astrophysics, you know, there's a lot of different uses of machine learning right now. I would say ones that I'm excited about. I'm not so excited about classification problems. I think most classification problems are kind of intermediate steps that maybe aren't so necessary. But I am very interested in outlier detection, which is a kind of classification. One of the things that machine learning is very good at doing is identifying when data look weird, because it's very good at capturing what's the structure of typical data. And so then it can find weird data. And a lot of interesting astrophysics has come from finding outliers. The discovery of quasars was stars that didn't look right. And that ended up being an unbelievably important thing in astronomy. So I'm actually slightly optimistic that outlier detection could be very important in the future of astrophysics. Lots of dimensionality reduction type things. I work on stuff like that because we want to have compact representations of our data, and those are often somewhat interpretable. They're interesting. We do a lot of label transfer, like you have some labeled objects, you want to label a lot more. We do that a lot. That's a problematic area. I am going to talk about that. And emulation, meaning you have simulations of the universe or whatever, and they're very expensive. Can you train a machine learning model to mock up simulations without spending all the computation? This is a very important area of research here, and I'm very critical of it, and I'm going to be critical of it going forward in this talk. I'll say, come back to that. Okay, so the core idea, which comes back to this whole kind of trust thing, is that machine learning does actually have a philosophy behind it. Actually, the funny thing is, here in New York, there was a conference on the philosophy of machine learning, and I couldn't make it to it. It was scheduled against some travel I had, so this is my philosophy of machine learning, not the philosophy of machine learning. But I would say that machine learning has two kind of really fundamental tenets to it. One is that your model is, the only goal of your model is to connect data to data. You have features and you have labels. They're both data, and you're trying to find a function which connects features to labels. That's just a data-to-data transformation. You don't have to understand what the transformation is on the inside. You just have to have an ability to predict data from data. So really the only thing that exists in this situation is the data, which is very different from the physics. In physics, the data are never our goal. Our goal is always to learn, I don't know, the age of the universe, or the nature of the dark matter, or how did the solar system form? We're not trying to just match data to data. We're trying to come up with an explanation, and our explanations are always in the latent space of the model, like the dark matter. We want to know where the dark matter is. The dark matter is like latent. It's like explicitly latent. That's what dark means. It can't be observed directly. So the ontology of machine learning is very different from the ontology of science, because in machine learning, it's just data. There's just data. And then, of course, the epistemology is that a model is good if it does a good job of relating data to data, and usually a good job in held out training data. So if you hold out training data, it does a good job of predicting it, then you say the model's good. And indeed, a lot of machine learning papers, the fundamental justification that their model is good is like a loss function on training data, on test data, on held out test data. That's sufficient in machine learning community to decide that a model is good. Again, very different from physics. In physics, we believe that a model is true if it is consistent with the data, but also consistent with all sorts of other theories we care about, and has latent structure that makes sense in terms of our other theories, and so on. So these are pretty different. Like, this is really a different world from physics. By the way, one of the things I try to be is interdisciplinary. I work in computer science, and I work in mathematics, and I work in physics and astronomy, and I try to be interdisciplinary. But machine learning is interdisciplinary in kind of a different direction, which is that machine learning methods, actually, some people have objected to this first line, mostly built by companies. Actually, many machine learning methods fundamentally come from academic work, but I should really say optimized. Machine learning methods were kind of optimized by companies for commercial applications. and they perform very well in those locations. And one of the reasons we're kind of very excited about machine learning is we see the high performance of machine learning in a project like TikTok, and we're like, well, that should have scientific value. But it's not obvious to me that being good at like delivering content to users or deciding what ads to show people or whatever is all that similar from science. So it's not even obvious that we should expect a usefulness of machine learning in science. Of course, not all machine learning falls into this category. It's much more complicated than this. Good. And this is just a repeat of things I've already said. Machine learning loves train, validate, and test. But in astronomy, we're usually trying to find new things that haven't been observed before or are qualitatively or quantitatively different from the things we've seen before. And another thing is that machine learning methods tend to treat the data as like given, as being like truth. The data are like the truth. Whereas we tend to think of the data as like a noisy, imperfect sampling of the world. There's selection effects, there's noise models, and we believe that there's an imperfection to the data. So those are kind of big differences there. And I think that probably carries over to most of the sciences. Good. So this now I finally made it to trust. So fundamentally, you can't really understand the internal properties of a machine learning method or why it's doing what it's doing or how it's doing it. And that statement is a bit controversial. After all, a lot of people work on interpretability. And I'm being a bit mean here saying that interpretability is a failure, that the interpretable machine learning has been a failure. There's probably people on this call who work on interpretability, and there are some interesting things that have come out of interpretability. Actually, I think interpretability as a goal has been great for machine learning because it's created a lot of interesting tools that we use to like go in and ask what's happening. But I don't think that we've succeeded in interpretation in the sense that when I even do large linear regressions, I can't interpret the coefficients. Some crazy linear combination of my inputs is a good predictor of my output. And I'm like, I change the data, the input data, and they change in unpredictable ways. And it's really not the case that we understand what these methods are doing. And I should say also from a mathematical point of view, a lot of the good mathematics on machine learning is really on very simplistic models. And once you're building like a 42-layer CNN, with fully collected layers at the top or something, nobody really understands why that object has the performance and properties that it does. So as I said at the beginning, where can you use a model that you don't understand? And that's kind of where I'm going. And I actually think, you can see that very positive or very negatively. The negative view is like, we shouldn't be touching things that you don't understand. Then positive view is actually there's lots of places in science we use instrumentation that we don't fully understand. And so there are roles. And here is classic. This is there. I could have figures like this from almost every domain of science now. Here on the left is a simulation of the universe. It's a simulation of a chunk of the universe that was done that took millions of CPU hours, maybe even tens of millions of CPU hours. It's a very, very big simulation. And then on the right is an emulation that emulates one of these simulations. And it's very promising that it looks like straightforward machine learning methods might be able to do it. And this emulation, to execute this emulation, training this emulation was expensive. But once it was trained, it can make a simulation output, a fake simulation output in CPU seconds rather than millions of CPU hours. So very promising. And this is big business in astronomy right now. I think it is in a lot of areas. I know it is in climate science. People are very interested in whether they could speed up the climate models. And there's a lot of discussion of like, what can you or can't you do with such objects? And whenever I see things like this, I always think of this problem. And this is the adversarial attack problem. And you'll see why these are related in a second. So this this is a classic paper. This is a screenshot from a classic paper from ICLR in 2015, but there's an enormous literature on adversarial attacks. This is like a very big area in machine learning. And the idea is that you can make incredibly small perturbations to your input data and often dramatically change the output. So for instance, this image, with the addition of this tiny bit of noise, this is a tiny amplitude times this noise vector, creates this image. And to any human, this image looks identical to this image. And I should say that noise vector was very carefully tuned. That is not a random noise vector. That was carefully tuned to fool the machine learning method that is labeling these images. And the image on the left is labeled as a panda at some confidence, and the image on the right is labeled as a gibbon at very high confidence. And roughly speaking, the way they did this was they optimized this noise to against the properties of the network, to push it in the direction that would make a wrong classification. And it's actually a little subtle how they did that. But this kind of behavior, when they published this, they were like, look, crazy. And then there's a lot of results. There was a lot of discussion of this. And most people in the machine learning community now see this as a feature of machine learning methods, not a bug. It really is just showing you that the models have immense capacity and they are summarizing their training data. And so if you move an image into a direction that somehow isn't represented in your training data, yeah, you'll get bad results because your training data are what rules. But I consider this to be very bad news for science. If you're using machine learning for science, if I think my machine learning method is labeling my images correctly, I think it's doing things like looking, oh, there's white fur. Oh, there's big black patches around the eyes. Oh, there's a little black nose. There's black ears. Oh, and there's a white belly. That's a panda. But that is obviously not what's happening, because everything I said about the left image is also true of the right image. By the way, if you looked up in your phone, what's a gibbon? I believe that the reason that this gets confused with the gibbon is that this part of the nose of the panda looks a little bit like the face of a gibbon. I actually think there's a mechanistic description of why this failure happens. But still, this failure shows you that the ImageNet model that was running here was not doing what you thought it was doing as a human being, or what you think you're doing as a human being. If you talk to a set of kindergartners about how do they identify a panda, they are not going to disagree about the image on the left and the image on the right. Good. So I believe that adversarial attacks reveal something. One attitude towards adversarial attacks you can take is, well, machine learning methods are, yeah, they're very complex models, and you had to search very hard to find these noise things that set them off. And so this isn't a generic failure mode. It's just some really obscure thing. That's one attitude you can take. But I don't like that attitude, because I think these adversarial attacks reveal that the model is not doing what we think it's doing. And that's pretty disturbing if you're using the model in a scientific context. If you're generating the large-scale structure of the universe with your model, you kind of want to know that it is actually generating something that's statistically equivalent to the large-scale structure. And if it was subject to an adversarial attack, you would be concerned. And there has been some work, actually, I don't cite it in these notes, but there's been some nice work by Peter Melchior's group in Princeton that shows that adversarial attacks do generically work against astrophysics applications of machine learning. Good. So this leads to, all of this leads to my first kind of technical point, which I think affects a lot of sciences, not just astrophysics. There's an attitude that people want to take, and this is true in climate for sure, and in astrophysics, and I think in a lot of areas. Simulations are expensive, also mechanical engineering type domains and materials science domains. Simulations are really expensive, so let's replace those simulations with an ML emulator. And simulations are really expensive. Like it's hard to capture how expensive they are. In cosmology alone, when we work in cosmology, our demands for simulations, if we really got all the simulations we wanted, it would actually take all of the computing capacity of the United States. Of course, we're not asking for that, but we could use it. If somebody gave the cosmology community the scientific computing capacity of the entire US, we would use it. We totally could use it. And I think the same thing is even more true in ocean science. Those simulations are extremely expensive. Ocean and atmosphere and coupled ocean atmosphere models, they're really expensive. And so easily they could use all of the computing capacity of the US. And so now what you say is, okay, it's too expensive, we're going to emulate, and you grind on your scientific problem using the emulators. And now imagine at the end of your project, you find something really surprising, like in astronomy, in cosmology, maybe you found that the sum of the neutrino masses that you can detect in the large scale structure is not consistent with the sum of the neutrino masses that you measure at the Large Hadron Collider. So now you have a real inconsistency. Maybe there's new physics. This might be a really important discovery that's changing everything we think about particle physics and cosmology. Super exciting. But then somebody could just say, well, maybe your emulator is not doing a good job. And you're faced with this problem of like, well, I guess we have to verify this result. But by construction, this number of simulations you need is larger than you have capacity for. And so we really would only check a result if it was extremely surprising. Like, it raises the bar for checking results. It raises the bar for computational science. And it raises the bar in such a way that we're only going to check really surprising results. And that really puts a grave danger of confirmation bias into our problems. And in cosmology, that's bad. We might get the universe wrong, but it's really bad in earth sciences, right? Because we're relying on earth science to guide us in one of the most important challenges that humanity faces. So this is something that I think one interesting thing about this is there's no real solution to this. Confirmation bias, you can't get around it by like thinking different. You really have to be somehow in a situation that every result can be checked independently. And it's not obvious that we can get into that state anymore, just because simulations are getting so expensive. This one problem with this comment is it actually applies more widely than places where ML is being used, but it's definitely very bad where ML is being used. Don't have a solution for this. I think it's super interesting. I think it connects to interpretability and explainability and things like that. So I think there might be solutions that help if things were explainable in certain ways. Okay, good. So let me switch gears a little bit to something that I do more on day-to-day. So day-to-day, here's a typical science problem that I work on. Typical science problem I work on is you take a spectrum of a star and you want to know that star's mass, age, and composition. Those one of the things that's very interesting about stars, for those of you who are not astrophysicists, is that once you know the mass, the age, and the composition of a star, to 0th order, you know everything about the star. So if you have two stars that have the same mass, age, and composition, they will basically very reliably have the same properties. They will look the same. They'll have the same spectrum. They'll have the same luminosity, same radius. Like everything about a star should be set by these things. To 0th order, there's lots of subtleties, rotation and magnetic fields and stuff, but to 0th order, that's true. So this is big business in astronomy, and there's been huge breakthroughs over the last few years because there have been big spectroscopic projects, some of which I've been involved in, SDSS 4 and 5, and there's a big satellite in Europe, it's actually a spacecraft in Europe, the Gaia spacecraft has measured 1 billion stars very, very accurately. And so this is really big business right now. And taking a spectrum of a star and inferring the mass, age, and composition of the star is actually very hard to do. It requires very good data, good judgment, and a lot of computation. And good judgment, because the computation is very incomplete and you have to understand what aspects of the computation are good and bad. And so it's a lot of work to very accurately determine the masses, ages, and compositions of stars. And so one of the things that has become kind of a cottage industry in astronomy is you get experts to label a few stars meaning like 1,000 stars. You get the community of experts to label 1,000 stars. And then you use a machine learning regression to label the remaining billion stars. I guess in the Gaia mission, there are a spectra of 200 million stars. So it's not a billion yet, but it'll be a billion at some point in the future. So 200 million stars, you only had to have your experts label 1,000, and then machine learning does all the rest. And that is a very exciting thing. Again, in my business, people are like, wow, machine learning is really changing the game. And I was one of the first people in this business. We have this project called the Canon. That was Melissa Ness in 2015. We actually did that work in 2014. And this plot, there's too much going on in this plot, but the 4 lines in each panel are 4 little segments of a spectrum of a star. That spectrum is very big. It covers a huge wavelength range, but these are just little chunks being shown to you for 4 different stars. And it's hard to see on this plot, but there's a black line and a cyan band. And the black line is the data for this star, and the cyan band is a generative model for that data that was trained on training data that these stars are not part of. So this is held out data. So this is that usual thing in machine learning. This is showing the performance of the model on held out data. It does incredibly well. And so we really can model stellar spectra very accurately and get parameters out of stellar spectra very effectively. And these are like X versus X plots. And one of the state-of-the-art things here is another project that actually I was involved in as well. Jiadong Li here made this encoder that encodes the Gaia data into a latent embedding, and that latent embedding can predict multiple qualitatively different kinds of data. It can predict stellar parameters, but it can also predict spectra taken by other instruments. And this is kind of like a baby foundation model. If you're into foundation models, this is like a baby version of a foundation model for stellar spectra. And this is kind of state of the art for labeling stellar spectra these days. But I want to say that, so this is great. I'm excited about this. I've spent a lot of my life doing this, but what is it actually a good idea? And I want to just throw a little concern. So if you want to do a joint analysis of many stars, so now I have 200 million stars. So now I want to do things like build a map of the Milky Way disk. I have 200 million stars. I'm observing them all over the Milky Way. Let's build a map. Well, that map is a joint analysis of those stars. If you want to combine data from multiple different sources, multiple different stars, you need to be multiplying together likelihood functions. That's like a basic point of statistics. Or if you're work with frequentist estimators, you need to be combining unbiased estimators or estimators that have where you somehow know and can correct the bias if you're going to multiply together multiple stars or join together multiple stars into a joint analysis. But if you think of it from a Bayesian perspective, you are updating a belief by multiplying together all the different likelihood functions from your stars. And it's extremely important, this point here. Almost no machine learning regressions or classifications return quantities that are related in any way to a likelihood function. They tend to return quantities that are much more like posterior quantities. And I don't know whether I say... So fundamentally, the reason for this is machine learning methods are making predictions, and the best prediction you can make is a biased estimate. Your best prediction of the weather today would be, might be based on the weather over the last few days, plus like historical information about today. And so you wouldn't just naively predict today from the previous days, you would also include a bias term where you're biasing your prediction. Predictions to have the best predictive value you always have biased estimators. Or another way to say it is there's a bias variance trade-off. And if you want high quality predictions, you're always working within the trade-off. You never work at zero bias. So when you take a machine learning method and you optimize it, you're always producing biased estimators. And this has a lot of problems. So just to be very, very concrete, if I had 1,000 stars, if I had 1,000 stars in one region of the galaxy, and I took an average age of those 1,000 stars, what would I get? Well, if I use maximum likelihood estimates, I would get an unbiased estimate of the average age. But if I take posterior estimates of their ages, I would get a biased estimate of the average age, because when I average those posterior estimates, I'm averaging the prior in over and over again. And so you're making a very biased estimate. And machine learning regressions generally return posterior, or things that are more like posterior estimates than they are like likelihood estimates. And that's a kind of subtle statistics point. It sounds too technical, but it's actually really important for the practice of astrophysics. And this is an absolutely ridiculous toy example, but let me just walk you through it. This is in an ICML. Oh, I didn't put the archive link here, but this is from I submitted a rant to the ICML, and here's like fake data. These are like artificially made spectra. So these are artificially made spectra. I made them by like some stupid piece of code. So this is like, I know the truth. This is all fake data. This is like a toy. In these data are encoded the ages of stars. So each of these is a star and has an age, and the age is in here in a way that's like a rectified function. So it's like a ReLU. There's like a rectified function that puts the age into these objects. So there's my data. And then here is the distribution of ages. So this is age on this axis versus some other parameter, like the position. Think of this as the position of the star in the galaxy. This is the age of the star. And the red dots show you the true relationship between position and age, the true average relationship. And then we train a machine learning method. And here's the input output of the machine learning method. Here's the true label. Here's the estimated label by the machine learning regression. I've used like a 3-layer MLP here. It's just a generic machine learning method, but you can see that basically we get predictions of the age that are reasonable. Not very high signal to noise, but age is a very hard thing to estimate. So this is actually kind of realistic from an astrophysical point of view. And now what we do is we apply, oh, and by the way, I just want to say here, the validation set and the test set are both drawn from exactly the same distribution as the training set. No cheating here. I'm not cheating in any way. The training set is a fair sample of stars. The test set is a fair sample of stars. The validation set is a fair sample of stars. Everything's drawn from the same distribution. There's absolutely no cheating. Everything is completely fair. This is the most fair test of a machine learning method you could ever use. And now what we do is we bin the data into these bins, and we ask, what's the average value of the age in each of the bins? And we get these X's. And notice they are offset from the true relationship. The measured relationship is offset from the true relationship, even though the labels are well measured, well estimated by the machine learning method, and the training data and the test data are drawn from exactly the same distribution. And if you look in here, it's a little hard to see. There's black squares in here, which are the means of the training data. So notice the mean values in the training data fall right on top of the true relationship, but the mean values in the test data do not. Everything's fair here. So like, what's going wrong? What's going wrong is that the machine learning method is trying to minimize the prediction error, and you minimize the prediction error by making a biased estimate. And things with large ages that get large ages tend to get biased younger, and things with young ages get biased older, because a biased estimator has a lower scatter against the true age. And so even though everything is fair in here, if we use these machine learning generated labels in our science, we actually get biased estimates. And that bias might not look very much to you. Bias might not look big to you, but there are many data points in this bin. And so this is actually very precisely measured. This this X location is, I think it's 30 sigma away from that red dot. So like we're talking about a huge mistake. And so there's a danger that astronomers are using. And one of the conclusions here is there's a danger that if you produce a catalog using machine learning, it might produce very, very biased scientific results. Because fundamentally in science, we're not trying to make the best prediction for a single star's age. We're trying to understand the relationships between age and other things. We're trying to understand these relationships using many observations. And so biased estimators can be very bad for us. Good. And I just want to say, I don't have a solution for this problem. You might think, oh, well, just like train it to make an unbiased estimate. But I don't know of any way to force a machine learning method to find an unbiased estimate. I don't know that that's even possible. And there might be a possible solution where instead of giving labels, you somehow learn the likelihood function, then optimize the likelihood function. And that project I showed called the Canon actually does build a model for the likelihood function. And so maybe it's going to be less biased in these situations. That's an open question. There might be, that's the only direction I have. But fundamentally, if you're just labeling things using regression, you are generating biased estimates. And it depends what you expect of your downstream users. Good. I want to make one last point. So those are two negative points. I just made two negative points about, emulators and about regression for label transfer. Let me make a positive point. And that is about like causal inference. So a lot of projects that I do in astrophysics could be described in the area of causal inference. If you look in the physics literature and the astrophysics literature, there isn't actually much mention of causal inference, but there are a lot of causal claims in the literature. So for instance, you measure the brightness of a star and it's got some wiggles in it. Are those wiggles in the brightness of the star because the star varied? Or are those wiggles because the instrument varied? And we can say, oh, I know for sure that it's the instrument there because the instrument has these properties, or I know for sure it's the star there because there's no way the instrument could be doing that. And in either case, you're making a causal claim. You're saying that this feature in the data was caused by a variability in the star, or this feature in the data was caused by a variability in the instrument. So I think we're using causal language all the time when we do astronomy. There's also lots of causal language just in the physical model. You say, oh, when a galaxy falls into a cluster, there's ram pressure stripping and it shuts off the star formation. People make kind of causal stories all the time in our business. And I think that's probably true in all of the sciences. In fact, I know a statistician who once said to me, I can't think of any important question in science that isn't fundamentally causal. I remember somebody said that, and I was like, what? And then I thought about it, and it really is true that a lot of the important claims in science are basically causal claims. We don't use this language as much, but the social sciences and the health sciences are very, very much about causal inference. Does this drug work? Does this intervention work? And we have our causal things are like things like I just said, was this caused by the star or the atmosphere or my instrument? If I'd observed longer, what would I have seen? That's a kind of causal question. And so one of the places which I just mentioned and I'm excited about is instrument calibration. So imagine we're measuring the brightness of a star. We're measuring it very, very sensitively. The reason I bring up this example is this is an example where we've worked explicitly with causal inference. And this is very big business in astronomy. If you're not an astronomer, measuring the brightness of stars is really big business right now. There's a satellite running called TESS that has been observing stars for years now, very sensitively. And the idea is to look for very small variations in the star's brightness, and they can indicate the physical properties of the star, and they can also show you that there's planets orbiting the star. So they're really important measurements. And it's very important to separate out the variations that are coming from the star and the instrument. And one of the things that when we say, we can confidently say that this feature is caused by the star and not the instrument. When can we say that most confidently? We can say that most confidently when we give our instrument model a lot of flexibility. The more flexibility you give your instrument model, the more surprising it is that your instrument model cannot explain the features you see, and you become more confident that they were caused by the star. See, there's a connection in causal inference between adding flexibility to your model and the confidence with which you can make your claims. And so this is oddly reversed from many situations in science. Here, you don't want to use Occam's razor. You don't want to use the simplest model you possibly can. You actually want to use the most complex model you possibly can, because that will give you the most conservative results about what caused what. And often, and especially in these instrument cases, you don't need to interpret the model. You just need to know that you gave it tons of flexibility. So in these instrument calibration situations are places where actually the ontology and the epistemology of machine learning is actually really valuable. We want a flexible model, and all we care about is matching the data. And if we can match the data, okay. But if we can't match the data, we have a very strong argument that that feature in the data was caused by something else, something other than the instrument. And that is a big area that I'm interested in and I work in. I calibrate instruments. Here's an example from an old mission by NASA called K2. And the K2 mission was the end part of the Kepler mission. The K2 mission, the satellite was not in a good state. It was in a bad hardware state, but they kept operating. And when they measure this is the brightness of a star, parts per million is the units. This is the brightness of a star. It's wiggling around. Actually, it's only thousands of parts per million. So this is actually still very, very precise measurement. But if you see these black dots here have a green line drawn through them, that green line is our model of what the instrument is doing. So this is talk about a flexible model. You see how flexible this model is. It really captures all of the, thanks, Matthew. It captures all of the variations of this star almost. And then when you subtract out this instrument model, you get a very, very clean measurement of the stellar signal. And we actually are able to interpret these features in this instrument model. This instrument model actually ends up making a lot of sense, but it is an extremely flexible model with I can't tell you offhand, but millions of free parameters. That brings us back to engineering a little bit. Machine learning is useful in the instrument calibration parts of experiments, precisely because the instrument calibration is part of the engineering infrastructure. Similar story can be told about backgrounds and foregrounds. I'm running towards the end of time, so I'm not going to go into detail. But for instance, when you look at the cosmic microwave background maps, this is the Planck data from the ESA mission called Planck, and these are images of the microwave background, which was created by the Big Bang, the light that's originally from the Big Bang, and it's contaminated by this stripe here, which is on this projection of the sky. This is the galactic plane. This is our own galaxy. And we kind of want to remove the galaxy and just see the cosmology behind. And that's another place where if you really want to know that you've removed the galaxy as well as you possibly can, you kind of want to throw the most flexible possible model at it. And that's another area where we use machine learning a lot in astrophysics. And it goes on and on. I have so many things to say. And I've said all of this before. The most conservative thing you can do in causal inferences is to use a flexible model. So I think I end up with open questions. The open question I'm focusing on is trust in emulators. Right now, emulation is clearly absolutely critical to the future of the physical sciences and maybe all of the natural sciences. It's obvious that emulation is here to stay. We have to figure out ways to make emulators trustworthy. I think this is a set of open questions. I don't even know how to formulate this as a well-posed open question. And I've been working on all these things: exact symmetries, adversarial training, sanity checks, and sparse resimulations, and I've been doing that with my math collaborator, Soledad Villar at Johns Hopkins. And actually, a lot of these issues of trust arise in artificial intelligence more generally, and in some ways, astrophysics and the other natural sciences can be a sandbox for thinking about trust in a bigger context. And that's what I said, and I'm done. Thank you.
Thank you very much, David. Great talk. So we've got time for questions for David. If you want to put your hand up or put in Aritra, please. You need to unmute yourself. There we go.
Thank you for the great talk. I had a rather specific question, although you're making a very general point in that slide where you're showing that biased estimate of ages. And you had that predictor kind of moving off at the edges of that distribution. Has that anything to do with the fact that the place where the estimates seem to be most biased are at the edges of the distribution of R values that you're using? For example, if I just extend that to 20 and I extend the other thing to unphysical -2, -3. Because we have seen this effect sometimes in other correlated work where the edges, it's weird. So I was trying to get a sense of
actually, in every machine learning project like this makes a plot like this of X versus X, right? It's like or Y versus Y, I guess, Y versus Y hat. If you look carefully at the plot, right, you can see the bias here, right? You see at this edge, all of the points are below the line, and at this edge, all the points are above the line. And this is absolutely generic in regressions. You can't really avoid this in regressions because regression, if you're trying to optimize a prediction score, you will always use a biased estimate, especially at the edges. It's so few of the data points have an age above 14 that if you're getting an age above 14, you're better to bias it downwards. You're going to get a better prediction score on average, you will, even though for the ones that are truly beyond 14, you'll get the wrong answer. I don't see, since the way machine learning regressions are trained is prediction score, I don't see any way to fix this. It's because you don't actually have access on any individual data point to the bias. It's only in a collective sense that you have access to the bias. Now, maybe you could add additional terms to the cost function that asked about statistics of this distribution. And maybe that would be possible. But fundamentally, it's similar to Bayesian inference, right? If you're doing a Bayesian posterior estimate, it's the estimate that wins bets, right? It makes predictions for the future, it wins bets. Those will be biased predictions.
Okay.
So I think it's kind of unavoidable.
Just to throw off an idea, in some of our work, what we have done is just said, for example, when plots like this come up for us, that anything which is less than 2, we can't really tell the exact precise answer, and we just throw that into a bin, that calling it less than something or greater than something. And yeah, that might be potentially one solution.
Yes, absolutely. And I think one of the things, I have a different talk about this area where I talk about like estimators, like what does it mean to make a measurement? And I think a big question is what do you expect of your downstream users? If you have a very high bandwidth channel to your downstream users and you can really explain to them how to use your data, then you can do complicated things. But for most astronomical projects, there's just these big catalogs on the web and people grab them and do things with them. And so I think some of it is actually just exactly what you're saying. It's just about like communicating really clearly with your users about what is and isn't believable in the data. I think that a lot of problems could be solved with that, I think. And we, of course, are working on that as well. And we're an open science group, so we're thinking a lot about how is information communicated about open scientific projects. And I think that's important, yeah.
Okay, John?
Yeah, if I can return controversy with controversy, and it sounds like what you're saying is it doesn't matter how you make your flat field so long as it normalizes the image correctly, which which is kind of hard to argue against, but it also trips my trigger of if you understood it, you could like replace the flat field screen and get a better calibration, or you could use a
Yeah.
lamp that doesn't flicker at a certain
Yeah.
um
Absolutely. We did this. There's a spectrograph at Yale called Express that we love very much. It was built by Deborah Fisher and her team. And I've been involved in calibrating that spectrograph. And everything we found in the calibration, Deborah being an instrument builder, she's like, I need to understand that. We have to fix that. We have to figure out where that's coming from and fix it. Like everything. And we're like, no, calm down. We can do it all in software. And she's like, no, that's not good enough. I need to understand my instrument. And she insisted on understanding everything. And of course, that was a hard task because we're using huge linear models that can't really be easily interpreted. But I'm very sympathetic with that because, of course, these machines do obey physical laws. They do have latent structure that's interpretable somehow. And I should say, this is not quite apropos of what you're saying, but like we can actually identify that each of these spikes is a thruster firing of the Kepler spacecraft. And so we can actually predict all the thruster firings. And actually, if you notice, they fire in one way on this part and fired the other way on this part. And that's because at this point, the solar torque goes to 0, and this has positive solar torque, and this has negative solar torque. Like this is completely interpretable, actually, which is actually goes against my whole story. So I'm very sympathetic with you that, especially if you're an instrument builder or you are close to the hardware, close to the pixels, you're going to want to interpret the things. But I think you're going to want to interpret it along very specific axes. You're going to want to ask, what depends on what? Like when we calibrated that spectrograph of Deborah's, we found that the thing that best predicted the calibration state of the instrument was the rate of chilled water flow into her optical bench. And she had all these temperature sensors, but it actually correlated better with the rate of water flow. And we think it's just because the water flow temperature sensitive valve was actually had higher fidelity than her temperature sensors. Like so I think I'm not against interpretability or not against interpretation. I think using the tools of interpretation to get what you can out of it. But at some level, if one person has an interpretable model that works pretty well, another person has an uninterpretable model that works very well, I'm going to go with the uninterpretable model just for my science. But I hear you. I'm not disagreeing.
Ashish?
Hi, David. Despite the good or bad in your talk title, I know that you are pro ML. You have been using it for a long time. So I should say that I said I'm a machine learning skeptic, obviously, from what I'm talking about, but I also use machine learning and I do a lot of machine learning in my research. Good, go ahead, Ashish. I just wanted. What are your top 2 or 3 caveats for using ML in astronomy?
I mean, I think a lot of it comes down to what Aritra was bringing up, which is that it's super important for us to learn some kind of language or words or ways of communicating about what is and isn't reliable and about the results. I think that's a really big question. And I think like adversarial attacks could have an aspect to that. These kind of estimator biases could have an estimate of that. And we could be somehow communicating better about what's the difference between a catalog produced by a machine learning regression versus a catalog that's produced by fitting every spectrum with a physical model of the star. So I think that would be my top kind of thing. What I'm currently working on is I'm working on places where we could structure machine learning methods to look more like physical laws, because I feel like if a machine learning method looks more like a physics problem, maybe it's going to give us answers that are more aligned with our physical. I'm thinking about like inductive bias, but it's speculative. I think the one thing I'm sure of is that if we had a better language for communicating about what you can and can't do with our outputs, I think that would be very beneficial.
Right. So I think what you are saying is that understanding the boundary conditions. So when we do interpretability or explainability, then we are thinking in very specific terms of what you have got, but also understanding what other ways things could go wrong or what other ways could have been contributing to whatever we got. So being more holistic and covering more dimensions that are where the problem is set, I think. Yeah, I think that makes sense.
Good. So let me say one very, very high level thing, which if I was talking about like estimators and measurement, it would have been like my opening slides. Very high level thing is all data analyses are subjective. Like a lot of scientists want to think, oh, I'm viewing objective reality, but any actual choices you make are subjective choices. And when you're building, when you're doing some big thing, like putting labels on all the Gaia data, I think it's a good idea to have in mind, what are the subjective needs of your users? How is this thing that you're producing going to be used by your users? Because if you can understand the subjective needs and interests of your users, you're going to do a way better job of A, giving them what they want, and B, explaining to them what the caveats are. So I think that would be my like translation of your word holistic. I'm like, I think it makes sense to think about the whole community of people who might be using your outputs and what they might be doing with them and how will those.
Right. Cool, thanks.
More and more questions. So we have a question from Slack, which was from Davey Poznansky.
Yeah, I see it there.
Yeah.
And he's saying that as models get more and more flexible, like it's great to find outliers with machine learning, but eventually if the models get flexible enough, nothing will be an outlier because they'll be so flexible, it'll just hit everything. And I agree. Actually, I'm struggling with that exact problem right now because I'm looking for stars with infrared excesses with Gabby Contardo. And we built a very flexible model for the stellar distribution. And if we build it flexibly enough, nothing's an outlier. And so there is a weird trade-off. I do think that there might be a different way of thinking about outliers from just asking, are they not fit by the model, but more like what tensions they produce in the model or how sensitive is the model to their removal. So like if a point is an outlier, the removal of that point will have a big effect on the latent space. Whereas if a point's an inlier, it won't have a big effect on the latent space. So we might want to think about outliers slightly differently going forward.
Yeah. Lee, you have a question?
Hey, David, good to see you again.
What's up, Lee?
So it's sunny here today. So my prediction is that it'll be sunny tomorrow and you should get on the plane and come on out.
I know. It's sunny here too, though, so you have some competition.
I mean, so that was really interesting. In the beginning, you made a distinction between prediction and understanding as the basis of a way to explain the difference. But really, isn't most of understanding just trying to get a better prediction? I mean, it's not really fundamentally, if you look at it in a different way, do you really ever understand anything, or you just understand it a little bit and then stop because it allows you to make a better prediction?
Yeah, it's a good question. I mean, if you want to get even more grandiose than I'm being, you could go to, the question of like quantum mechanics. Does anybody actually understand quantum mechanics, or do they just know how to calculate? The kind of shut up and calculate attitude. But I still think there is a big difference because, when you're talking about quantum mechanics and talking about what you know about the world, you're always talking about the latent structure of the model. You're not talking about the readings on your voltmeter. You're talking about the wave function and the different states and the sum of states, and you're always talking about things. So we are attached to reality. We do need to make good predictions. It would be terrible if physics did not make good predictions. But I don't think the biggest breakthroughs in physics are actually predictions. I think they're more like latent things, like
perhaps. Now, you could argue that what's driving it is the desire to make the prediction that you could.
And I think there is a spectrum of physicists, and definitely there are some that are more on the side, and maybe I'm even one of them, that's more on the side of making good predictions. Yeah, I think there is a spectrum, but I think when people kind of summarize the key results of physics, we don't tend to summarize it in terms of the data we predict. We more summarize it in terms of the consistent like latent structure, like the standard model of particle physics.
Perhaps we're just fooling ourselves also.
Well, right. I mean, and there are actually interesting situations where the data are strongly in conflict with the models we care about, and we go, well, yeah, it's these other things, these auxiliary things we don't fully understand, blah, blah, blah. You know, so there it is an interesting thing where there's a lot of back and forth in physics between the data, old data, new data, and the latent structure of the models. And the big, and frankly, the big breakthroughs of physics have often been big changes in the latent structure of the model, like going from Newtonian gravity to GR. All of a sudden there was a space-time and a metric, and you know, like it was a very different picture of gravity. Anyway, I think,
but a better prediction of what.
But it was also a better prediction. Exactly. Right. It subsumed all the current predictions and made a few more.
Right. You're right. You're right. That was very good.
Yeah. Anyway, yeah, good. I think it's complicated, and you can take a hard view that it's all about prediction. I don't agree with that, but you can take it.
Right. Okay. We're 10 minutes past, so we'll call it there for today. Thank you again, David, very much for this excellent talk.
I think I can make this.
The talk will be posted on YouTube in the next 24 hours, and our next talk will be on April 8th, I believe it is. Same time. And
total eclipse. Don't conflict with the total eclipse. I think this is about when the total eclipse is happening on April 8th.
Yeah.
You might have to move it by now.
Might be the case. We may want to do that. But our next speaker will be Adam Charles from Johns Hopkins, who will be talking about machine learning and biomedical engineering. Okay. Otherwise, thanks everyone, and we'll see you soon.